what it says here, basically, I've got my two vectors, A and B, and there's an angle theta in between. They both are in the same plane. Same plane means it's 2D. So A cross B give me a vector C. The vector C has got a direction which is in the positive y direction. So how do you figure out the direction? Is the basically the right hand rule. You curl the direction of your fingers in the direction of the cross rotation, that is from A to B. You curl your fingers from A to B. The direction of thumb gives you the direction of the third vector, which is C. So if I do B cross A, which means now with the right hand, I am going to curl my fingers from B to A. The thumb will be in the downward direction. And so therefore, C is equal to A cross B, both the vectors, which is also equal to minus B cross A. I'll show you in the next slide. I guess I've got it in the next. Yes, I've got in next slide. So I'll show you this in the next slide. So remember, C is A cross B, and the direction of the C you can get it from right hand rule. The magnitude and direction of the resultant vector A cross B. You have to remember this. I'm not going to go into the details. You already know this. A cross B, the magnitude is AB sine theta, and UC is the unit vector of the direction. That is basically, in this case, pointing upwards. So you have to remember C is equal to A cross B, which is equal to AB sine theta multiplied by the unit vector of C. Or, in simple words, M moment vector equals R cross F. What happened to R? Okay. R cross F, which I can also write as R F sine theta and the unit vector of M, which I'm going to show you in the next slide. So what you need to remember is this. It says here that UC is the unit vector perpendicular to both A and B vectors as shown. And okay, so now let's look at the direction. Commutative law. Commutative law doesn't apply here. So let's look at this one. Let's look at this one. It says A cross B. So I curl my fingers from A to B, and the thumb points upward. So my C is in the upward direction. What if I do B cross A? I'm looking at this one now. B cross A. So I curl my fingers from B to A, and the thumb is now downward direction. Therefore, commutative law where it says A cross B equals B cross A does not apply to cross products. But if I do this, C is equal to B cross A, which means it's pointing downward. But if I put a negative here, then it means it's on the other side then. So I won't go into the details. I'm also, you know, the associated property. I already know this. I won't go into the detail as given here for you to go through. I won't even discuss it. You've already done this in school many times. Excuse me. Okay. Distributive law also given here. Won't go into the details. You already know this. So the right-hand rule is a useful tool for determining the direction of the vector resulting from the cross product. So a vector crossed into itself is 0. Okay, let us first look at this. Let us first look at this, what this means. I'll go back to this one. Oh, no, sorry, to this one. I'm looking at this figure here. So this, if this is my x-axis, This is my y-axis, then this is my, this is my z-axis. Okay, so C equals A cross B. So I curl my fingers from A to B, that's from here to here, and C points upward. C is in the direction of Z. So as it says, I cross J equals K. Okay, so going back, I cross I, remember I cross I, you can figure it out. I, sine of 0. Sorry, sine theta, sine of 0. What sine of 0?
0.
0.
Is 0. So therefore, remember, a vector cross into itself is 0. And this is the diagram I want you to memorize. So if you do I cross J, the answer is K. When you do J cross K, the answer is I. Similarly, if you do K cross J, the answer is minus I, and so on. So remember this. This is a very good tool. So you will not get confused if you remember this. Just to summarize, as I said, I cross J is K, I cross K, the opposite is minus J. And if a cross product of itself is always equal to 0. So if I do A cross B, which is given here, and this is basically the expanded version of it, where I omit all those identical ones. My final answer comes out to be this. There's no rocket science, it's easy. You will not be able to memorize, don't memorize it, it's A cross B. Let me make life easy for you. Remember this matrix? You can also write in this form and find the determinant. I'm not going to teach you a determinant now. You already know this. So for the I component, you got this value here. For the J component here, you know this, why there's a negative here. And then for the K component is here. This is exactly the same as given here. Okay, so in simple words, what is saying that you can do A cross B by matrix in getting the determinant of 2 by 2, you can get the answer for each component of the Cartesian. Is that clear to everyone?
Yes, sir.
Okay, so let's move on. Okay, moment in 3D. The reason why I was spending time on matrix and the vector cross product, that's because the cross product of two vectors was needed for calculating the moment. Okay, so what we have got here, very interesting situation. Excuse me. We've got position vector R, and we've got a force vector F. How are we going to find the product of those two? So it says here, moment in 3D can be calculated using scalar 2D approach, but it can be difficult and time consuming. Thus, it is often easier to use the mathematical approach called the vector cross product. Now you understand why you are learning cross product. Using the vector cross product, that's here, where R is the position vector from point O to any point, gentlemen, it's any point on the line of action of F, any point on the force line. any point on the force line. What that means, let me go back and let's look at the give me a good picture. Okay, I'll use this one. Excuse me. Okay, so we did here m naught equals r cross f to find moment. Okay, I can do this. Look, that's my first line, and I can take this as an r1. So I can write m naught equals r1 cross f. They both will give you the same answer. I can even do this. Watch what I'm doing. R2. These are position vector, okay, gentlemen? Sorry. So I can also write m naught moment at point O equals R2 cross F. So basically, moment is the position vector on the force line from the point where you want to measure the moment. So let me go back to the explanation given here. Yes. So remember here, R is the position vector from point O, where you want to measure moment, to any point on the line of action of your force vector. Is that clear to everyone?
Yes, sir.
Okay. Okay. So using the cross product, a moment can be expressed in this form. You can expand it by two by two determinant. You can get this, and the physical meaning of the above equation becomes evident by considering the fourth component separately using a 2D formulation. So in simple words, what I'm saying here, you got this moment. What is the real meaning of it? As I said, students are very good in calculating numericals, but they physically do not understand the meaning of the equation. They can solve the equation, but they cannot create an equation out of the real world problem. Now, question is what this means. What is it means? So we'll have a look when we consider in 2D. So I have got let me see. I have it. Yes, I have it here. I found this. That's good. So moment matrix 2 by 2 determinant gives you this. So let us see what is the meaning. I'll just pick any one. What is the meaning of this one? Let's look at this. What is the actual meaning of this? Before I go into the details, let me draw a bar. Distance is d. I'm applying a force here, and I'm writing m equals fd. You can easily visualize what this means. This means it's a bending force, F into D, moment. It's a bending force trying to bend this rod. Am I right?
Yes, sir.
Okay.
Yes, sir.
So you know what moment is. It's a bending or turning moment. So let's now look what this means. This is related to my x-axis. So where's my x-axis? That's my x-axis here. So it means that all the forces which are trying to rotate the object along my x-axis, my center of rotation is x-axis. Okay, this one I am explaining you the importance of this one, the physical meaning of it. It means all the moment that is trying to rotate in this way, where the center of rotation is my x-axis. Okay, so let us look at this term first. The first term here, this one, ry f z. So where is f z? F z is here. That's my f z. Remember, we are looking at the rotation caused along the x-axis. Okay, that is my f z, which is a component given here. This is my f z arrow, and the distance is ry. This is my ry here. So I can draw it here. That's my distance, and this is the force acting upward here. So if I look at this force, I'm looking at this force. So there's a tendency to rotate it along x-axis. Am I right?
Yes, sir.
So anyone who didn't understand this, you can raise the flag. So remember, what I am looking at, I'm looking at
सर थोड़ा सा ये दोबारा समझा दें.
Okay. देखिए ये moment है. This is the moment. Okay. So we've got three terms. Okay. I am just looking at this term. I want to find what is the meaning of this term. So in this term, let me first look at this. What is Fz? Fz is this force, so that's my force line. So that's my force line. And the perpendicular distance from x, this is I, okay? So perpendicular distance from x. So my perpendicular distance would be this. That's my perpendicular distance. So this, if I look at the diagram, at this part of the diagram, it says that I've got my ry, which is the perpendicular distance, which is this one, multiplied by my fz, which is this. This is my fz vector. So if I look at the perpendicular distance, now I'm concentrating here. So if you look at the force multiplied by perpendicular distance, you can visualize there's a tendency to rotate along my x-axis. Is that clear?
Yes, sir.
Yes sir.
Yes.
So I'm at the moment looking at all the forces that is trying to rotate my x-axis. I'm looking at all the forces, all the moments that is trying to rotate my x-axis. So I looked at Fz. So that was this part. Now let us look at this one. So that is Fy. Where is Fy? This one is Fy. So I have my force line here, and its perpendicular distance from my x-axis. So that's the perpendicular distance, which is given. Which is given here. That's my Rz. So let me make it more clear. So my Fy is here. That's my Fy, and my and my perpendicular distance, that's this distance, which is the same as here. This is my Rz. So that's my Fy, which is here, multiplied by the perpendicular distance, which is Rz. Okay. Now let us see what is this going to do what's going to do to my x-axis. Now I can clearly see it is trying to rotate my x-axis in this direction. Am I right? Can you see that?
Sir, how can we determine that a
Yes, sir.
horizontal force is moving the body in clockwise or anti-clockwise direction?
Yes, that's because look, the force is here in that direction. That's the direction of it, and it's perpendicular distance from my x-axis. So it can clearly tell you it is rotating in this direction.
Okay.
Okay.
Like we
So
have to see towards the on which side lies the perpendicular distance from the line of action?
Yeah, the force vector. So basically, you do not need to do that because your calculations will give you the answer. I'm just telling you the visual effect of this term here. So I've got my Fy acting in this direction. That's my perpendicular distance from my x-axis. So rotation is in clockwise direction. Therefore, it's a negative sign here. But if I look at the FZ, which is this one, that's my FZ, and this is the perpendicular direction, and it is trying to rotate my x-axis in this direction. That's anti-clockwise, therefore it's positive. Now let us look at the effect of fx on the rotation of my x-axis. Now fx is in parallel with my x-axis. So it cannot rotate my x-axis, it rotates the y-axis. So therefore, in the I term, there are two terms. And in a very similar fashion, these are basically the other moments created for different axes. So in simple words, what it says here that this term tries to rotate my x-axis. This term is trying to rotate along y-axis, and this term is trying to rotate the object along x-axis. And that's basically the details given here. Is that clear to everyone?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Okay, gentlemen, just give me a minute. I need to take the attendance. Okay, so where is it? Come on. Okay, gentlemen. So we will stop here now, and we'll continue next week. I'm going to put another assignment on Teams. As I said, it's very unfortunate. I cannot have a class assignment. So keep an eye on Teams. There'll be another assignment being uploaded on it. So far, any questions before I end the lecture?
Sir, I have a question.
Yes?
Sir, before this lecture, we were talking about clockwise and anti-clockwise movements.
Yes.
So, in this lecture, we learned that the actual direction of the torque is perpendicular to both the distance, moment arm, and force vector. Okay.
Yes.
So what do we say is the direction of the torque, the perpendicular one or the clockwise or anti-clockwise one?
No, it's the clockwise, anti-clockwise. It's the tendency of rotation. You need to realize the ten. Let me quickly explain it here very quickly. Or do I have a clean? I have a clean. Okay, I'll do it here. So, watch. That's a point, and I want you to calculate. And I'm okay. This is a bar. Let me see. This is my bar. It is pivoted at the center. I'm applying a force F here. Okay, and this distance is 1 meter. Force is 10 Newton. So moment at this point center will be moment at O will be 10 Newton meter. Am I right? So what is the tendency? Is trying to rotate clockwise, so this will be negative. Clear? Okay. Now stay with me. Okay. Now watch what I'm doing. I'm applying the same force here. F is 10 Newton. And the distance is also same, 1 meter. Now my moment is the same number. It is the same number, but does not have a sign. Come on, get rid of the sign. Yes, because the tendency is to rotate counterclockwise. Is that clear?
Yes, sir.
Okay.
But the direction of the moment is perpendicular to both r and f vectors.
Yes,
And the
yes. The
tendency
cross,
to,
yes. Yes. Okay. Yeah. In this case, the direction is coming out of the screen. It is perpendicular. Yes. It's a way to visualize the direction. Yes, I understand what you mean. That the direction of this is basically a vector that is coming out of the screen. Is that what you're saying?
yes, sir.
Yes, that's a way of describing it, because in 3D it will be very difficult to see the clockwise and anti-clockwise. So therefore, they define the direction of the vector in with respect to the third component, which is basically coming out or going into the screen. So that's basically when you do when you're doing finding resultant of different moments in 3D. That is a very useful tool. Is that clear?
Yes, sir. Thank you.
Okay.
Sir, I also have a question.
Yes, please.
Sir, when we are calculating the moments and our total moment of the system is negative, so
Yes.
do we keep that negative sign in our final answer, or just as we write the magnitude, we keep it, we just remove the negative sign in our final answer?
No. Keep the sign there. Keep the sign
Okay,
there.
okay, sir.
Yes. It's
Thank you.
important. Keep the sign there, because in the textbook you would see they sometimes write like 10 Newton meter and they put a symbol like this. I will not suggest to do this. The best thing is to put sign here.
Okay, sir. Thank you, Lord.
Okay.
Sometimes like they even write counterclockwise or clockwise over there completely instead of just the arrows. So if,
You're saying to write clockwise, anti-clockwise?
yeah, because I've seen a few questions and they were like they wrote the magnitude and then right beside the magnitude they wrote counterclockwise or clockwise to indicate the direction instead of making the arrow or the sign.
Yeah, look, if you start writing text clockwise, anti-clockwise, there's a possibility to make mistakes, because if you got a lot of moments acting in 3D space, then for each moment, instead of putting signs, you will write clockwise, anti-clockwise. And when you're going to calculate the resultant of moments, then you will need to realize if for clockwise, I have to put negative or anti-clockwise. So the best thing is when you calculate the moment, put the sign there.
Yep.
Okay.
Thank you.
Excuse me, sir, I have a question.
Yeah.
Sir, the question is that if you're observing moment in 3 dimension, so from a observer who is standing in front of a rotating object, the rotation will be in one direction. But to an observer who's standing directly behind that rotating object, the rotation will be in the opposite direction.
Yes.
So if they do calculations for a moment, they will have opposite signs. So which one? What
No, they
convention
will
do we
not.
choose?
Yeah, they will not make a mistake, because remember, to solve any problem, even any real life problem, the very first thing you need to do is to define the axis. Then you start solving your problem. So for the XYZ component, wherever you're looking the coordinates from, your XYZ will remain there. Therefore, they always say, before starting any problem, define your axis.
Okay, sir.
Okay.
Thank you.
Okay, gentlemen, we have to stop here. So, inshallah, I will see you next Monday then. Thank you very much for your time.
Excuse me, sir.
Yeah.
Kindly mark Muhammad Sumran Shahid as present, because there's some issue with his account, so he's joined as a guest.
Sorry, what's the name?
Muhammad Sumran Shahid.
Shahid. Okay, I'll do that. Okay.
Thank you,
Sir,
sir.
one last question.
Yes.
Sir, in our assignments, do we need to follow the particular pattern of solving the numericals as it is mentioned in the slides, or we can just do it with another method if the answer is okay.
Yes, you can use any method which you are comfortable with.
Okay, sir. Thanks a lot.
Yeah.